Imagine xn represents the number of individuals alive in generation n. So if I have an nth generation going on, it depends the number of people alive on the nth generation. Are you guys with me? So why this? Would this be a Markov chain actually? Think about it. Number of people alive in that generation. Why don't we have a progeny? We have some calf, nation that. And we are saying that how many, people will be alive in, for example, in Pakistani nation or in some cost, after say 11 generations. The answer is, I have no idea. But I know one thing for the fact is that it depends on the 10th generation. That's what would happen in the 11th generation. So how many people are there? Okay. And it doesn't depend now actually. Okay, we can do things now. For example, you have Japan. Japan has a serious crisis actually. So in Japan, you have the majority of the population who are old actually. Okay, and the youngs are not ready to raise the kids. So they are not interested in raising the kids. What happens? What does it mean? It means that eventually the population will reduce actually, because the youngs won't have time for time to spend on the kids actually. So they are not interested in the kids.
फिर भी वहाँ पर जो present आएगा उस पे depend होता है.
इस पे depend करता है. Okay, so it depends on the present, but what was the population of 100 years before actually? It has nothing to do with it. It has nothing to do with it. So this would be it. You can precisely formulate it, but this would be an example. Markov chain. What would be the potential state? What would be the potential state? Always be it should be 0. 1, 3, or so. Okay. You can find many examples. Markov chain. You can think of, you can almost imagine that you can think of many examples. Just think about it where things are not dependent on the past but depend on the current state actually. So in other words, the revenue that the PIA is making every year depends on its state now. It doesn't depend on what was PIA in 70s actually. Okay, national airline was it depends on now. We make a prediction. You can't. So in other words, this 30 years information is irrelevant. 30 years, 40 years. Though it's not truly irrelevant. There is always relevance, but for practical purposes, it's not. So here is some notation. Imagine on nth state, so I have a Markov chain or a Markov process. Okay, better to call it a chain. But the process of well. Imagine in the nth state, so we Markov chain and Markov process. In nth state, you were in the state I. The process was in the state I, and I can be anything there. And in the nth state, you are at J. It's not necessarily.
No,
I.
the J bigger than.
Could be less than I as
Less than
well.
I
You have no idea, but the only thing that you should have is that I and J are from their states. Okay. Then we'll denote this probability that Xn is going to be J, given that it was previously I, we will denote it by Pij. Okay, Pij. So this probability or such probability, we will call it a transition probability. So it's a transition probability. Okay. So it's like a probability that the chain or the process will transit or make a transition from the state I to the state J. And we will say that a process is a Markov chain is time homogeneous. Okay. Time homogeneous. Okay. Are Xn as stationary transition probabilities if these Pij's it does not vary with time. Does not vary with time. So what do you mean by that? Okay. So in other words, the probability that the weather going from dry to wet is 1/3 today. Okay. So if I assume that it would be 1/3 forever, it is not a good assumption. Okay. You have environmental inequalities, things that can variate these probabilities, but for the sake of simplicity, we say that if the probabilities of transitioning from one state, so for a process, if the probability for transitioning from one state to another state are not changing over the time, you will say that it's a time homogeneous.
For every ij
Time Markov chain, okay, so time homogeneous Markov chain. This Markov chain has a stationary distribution. Okay. The good thing about this is that in the study of Markov chain, so obviously, as I said, the fundamental question that we will be interested in, while studying the Markov chains, is going to be that what would be the long-term behavior of such kind of processes. So we know the long-term behavior for the IIDs, so you have law of large numbers and central limit theorems giving the answers. But if you have such kind of process, what would be the long-term behavior of these probabilities? Distribution of. So that's what is the fundamental question that we are interested in asking. So the good thing about Markov chain is that you can bring in the matrices actually into the action. Let's look at you can bring in matrices. How? So imagine if I have a state space S, okay, takes these values, then I can write a matrix, which I'm going to call a transition matrix, and is going to have entries actually. Okay. So the first is going to be P00, probability that you are in state 0 and you will be state 0 in the next movement actually. P01, P02, and so on and so forth. Similarly, P11,
1 0
0,
1 1.
1, 1, 1, 2, and so on and so forth. So this is what we call a transition matrix. Here's actually. Okay. What would be the key property of the transition matrix? The key property of the transition matrix is going to be that each of the row has sum equal to 1 actually. So if you sum up all these probabilities, okay, it's if I say P, if I sum P0I equal to infinity or finite, whatever, it should be what do you call that? So that's what make it something, what do you call this, stochastic matrix. Stochastic matrix.
सर टाइम होमोजेनियस केस में सारे एंट्रीज की एक ही वैल्यू होगी
एक ही होगी. So this would not evolve over the time. So if this probability is 1/2, so it would stay 1/2 forever actually. Okay, so that's what essentially. So it doesn't changes as time passes. So, but for rows, I know for sure that it is. The last thing that I would like to talk about, say, is this symbol P-I-J and putting an index but in bracket after. Okay? What does this mean? This means probability that the chain would go from state I to state J, not in one step but n steps. So n steps. So what do you mean by that? So what would be the meaning of P132? So this means that you are in state 1 and you will be in state 3 in 2 steps. So in step, so if currently I am at, for example, state 1 and so in the first step I can be anywhere. So I can be on 4 or 1 or 3 or I can be anywhere. But in the second step I'm reaching to. So this represents, so how can I write a probability that currently, so imagine currently at mth moment I am in the state I, okay, and so what would be the time after the n steps? So it would be m plus n. So after the n step, I will be in j actually. So that's what it represents. Okay. And so similarly, I can define P, with this script in the bracket, so that contains all such probabilities. So in other words, this is the Bij, okay, and where I and j are from the state space. So this is a bunch of that we have. By the way, tell me that since all these are probabilities, they must be non-negative. Okay, and the matrix is stochastic active.
सर इसको एक बार फिर से आप अगर वो जो आपने टेन वाला लिखा है इसको अगर इंटरप्रेट करें.
So the probability that currently I am in the state I. So there are two things. One is the state, another is time, the movement actually. Okay. So since it's a stochastic process, so it must be related with some movement actually. Yes. I mean, even this n is, this subscript n is really, in a stochastic process, subscript n is, like these guys are really abstract things. So you can interpret them as time, but if you have some other interpretation, you also can have interpretation.
Sorry.
Okay. And some other value that, and I and j are the values that, these random variables take at the different times. Okay. So what this is telling you, imagine at the moment I am on the state I, but I don't know what time is that actually. So therefore I'm substituting m actually. And I'm interested in computing the probabilities that after the n steps,
I will be at j.
All the, this step could be, or after the n instant, this step could be n, n gains, or maybe if you are checking the whether early and hours, or if you're talking about the population after the n generation, I'll be in the state what you call j. This time should be withdrawn. Yes, so this should be fine. Okay. This probability would, at the moment this is just stationary, and it would depend. So currently, if you are here and this is future, so this would only depend on m. Okay, not at the previous instance actually. M minus 1 से लेकर 0 तक इसको will depend on m. But obviously, if this m become m plus 1, so it would also depend on m plus 1. So we will write the expressions for it explicitly, and you will see that if you want to compute such probabilities, we need to have something what we call the judgment column of permutations actually, and they will allow you to compute such probabilities.
Sir, stochastic matrix क्या होता है?
Stochastic matrix is the matrix in which the entries are non-negative, all, and the rows or columns, whatever convention you are using, must have sum equal to 0. Sum equal to 1. Okay. And why that should have a sum equal to 1? We will think about it, or we will discuss it.